You thought it was before you the plates. We have to be realistic. You'll never get.
So good.
I'm writing a sequel right now. So favorite.
Do you switch the answers?
Not within a game. Usually just whenever like I'm too busy to run something and somebody else will step in or something like that.
So they would borrow your notes.
No, entirely. Like it's on.
Yes.
I think it would destroy me. It's like, I think it would destroy my life.
It does.
Yeah.
I think I should put down, they have D&D sessions on my application here, so that I can.
Brad was just showing me his folders to each one, and it was like, hey, it cost 93 hours for this little thing. Like, oh yeah, that doesn't even count the ones that I've redone.
Right.
I think I just hit the 90-hour mark on my.
Yeah,
I have a thing to
Yeah.
show you.
1 week ago, when you need to.
Is it also HD?
No,
I love.
It's not folders gaming, but it's
It's
a
for how long?
Reddit, like,
Right.
gimmick thing that absolutely, I cannot stop thinking about it.
Wait, is this not?
No, in alchemy job. Every week.
Do it.
You know, yeah.
Some people.
So I saw the title of the mayonnaise. So, wow, pretty awesome. But it's more than that. No. It's like more than that.
Yes.
What do you teach?
Alright, we are
I
at
think
30
what you
minutes.
thought. All right, let me get those.
So I'll go ahead and start. Can I acknowledge them? Start webinar buttons. Okay. All right. All right. Hey, everyone. Thank you so much for coming out today. We really appreciate you coming to the library. And the library also appreciates our longstanding partnership with Science Bubble. I don't know how many years it's been, but at least like 7. It's been a lot. So it's exciting. So I'm going to do a quick land acknowledgement, and then I'll introduce our Science Bubble team, and then we'll get to the speakers. So Berkeley Public Library buildings are built on the territory of the Huichin within the homeland of the Chochenyo-speaking Ohlone people. We acknowledge and honor the Ohlone people who have lived in Berkeley and throughout the East Bay since time immemorial. The library recognizes that Berkeley residents have and continue to benefit from the use and occupation of unseceded stolen land. And we pledge to recognize the permanence and the rich contributions that the Ohlone people continue to bring to the city of Berkeley and throughout the East Bay. We celebrate the strength of the Ohlone people and their culture. And the Berkeley Public Library is committed to helping create a more just and anti-racist society and to furthering the visibility and celebration of Ohlone authors who are specific to the East Bay and Ohlone culture in our collections and programming. All right, so welcome to the Science Bubble, folks. This is a monthly seminar series that aims to share new research findings from grad students and postdocs at UC Berkeley with the general public and create constructive discussion about a variety of science topics. We have 2 speakers at each seminar who will talk about their current research or a topic that they find really interesting. The organizers are 3 graduate students at UC Berkeley, Kaylin Zong, Daniel Bretthauer, and Madison Leamer. Lectures happen on the 3rd Tuesday of the month at 5:30 p.m. here and on Zoom. The programs are live streamed on the Science Bubble YouTube page, so you can view them later and share them with others. Popping the Science Bubble also has a website and a listserv that you can join to keep up to date on Science Bubble lecture topics.
I'm gonna give the phone to Ken.
All right.
I'm gonna be more helpful.
Let Daniel introduce tonight's speaker.
So as Kelsey said, we'll have a QR code at the very end. If you want to, you can sign up for our listserv where you can get more announcements and all of that stuff. So for tonight, we're excited to have both Stephanie Ribet and Natalie LeBaron presenting tonight. So this is an open format talk. So if you have any questions during your presentation, please raise your hand, and when time's appropriate, people calling you to ask a question. And so for those of you who are on Zoom, you can also submit your questions to the Q&A function there, and we will get to them at the end of the talk, where we'll read them aloud. And there will also be time at the very end of each talk for questions as well. And so to start us off, tonight's first speaker is Stephanie. And so Stephanie grew up here in Berkeley and then attended college at Princeton University. After working for a few years at a battery startup in Michigan, she completed her PhD at Northwestern University. She is currently a postdoctoral researcher working at Berkeley Lab at the National Center for Electron Microscopy, which is part of the Molecular Foundry. When she's not in lab, you can find her running on the fire trails and reading for her fiction. So without further ado, please take it away, Stephanie.
Thank you guys for organizing this and for setting this up. This is a pretty cool activity. So I'm going to be telling you about the work that we do at Berkeley Lab at the National Center for Electron Microscopy and the type of imaging I do. I do very high resolution imaging, and I do this with an electron microscope. As you said, I was going to introduce myself. So I grew up here in Berkeley. And so I'm extra happy to be back here at the Berkeley Library because I've been here a lot as a kid. I asked my dad, who is sitting right over here, for see if he had any photos of me as a kid, like hanging out at the library as evidence that I've been here or something. And the best we could do is find a photo of my sister at the Contra Costa County Library. So who is the reader in the family? And unfortunately for you guys, it's not me. But so I grew up in Berkeley, and then I went to Princeton for college. I worked for a few years doing battery development, and I liked that a lot, and that's what led me to do my PhD. And I did my PhD at Northwestern, and that's where I started doing electron microscopy, which is what I'm going to tell you about today. And then I moved back here to Berkeley Lab, and Berkeley Lab is a really awesome place to be doing these kinds of measurements and these kinds of experiments. And mostly what I'm going to tell you about today is what we do at Berkeley Lab. So I'll start by telling you about the center I work at. This is the National Center for Electron Microscopy. It's part of the Molecular Foundry. If you've driven up Centennial and seen this sort of weird looking building, this is where the center is, or where the Molecular Foundry is. We're right next to it. And where we work is a user facility. So what's cool about that is it's free to use all the microscopes and all the tools, and people submit proposals, and then an outside committee decides who gets to use the equipment. So of course, a lot of our users, it makes sense, come from Berkeley and the university and the lab. But we also have people coming from all over the world. So that's what I like a lot about my job, is getting to meet people and see what people are working on and learn from them. I wanted to tell you kind of briefly what it's like to work in the lab from beyond the science. So this is sort of what it looks like looking out of our building. I guess I was there pretty early one morning. You could see the sunrise coming up over the base. That's pretty nice. Depending on who gets there before you, this is what your desk may look like when you arrive at the lab. And then not all of our users are strictly human. We have some really great visitors to the lab as well. So we have these turkeys, and then of course, safety first. So we have goats that come and eat all the vegetation for fire safety at the lab as well. So it's never boring. From a science perspective today, what I want to talk to you about is imaging at very high resolutions. So I thought first I just sort of briefly explain to you kind of what length scale we're talking about and give you a sense of that. So kind of starting from the length scale that you may be more familiar with in everyday objects, this is my example as a volleyball. We can move even smaller. And my next example of something smaller than that is a euro coin, so still an everyday item that you might encounter. Going even smaller, we get to a grain of sand. We can get even smaller, and now this is something that I think of one of the smallest things you can see by eye is a human hair. Again, going smaller, you get to the red blood cell, and then a bacteria. Even smaller to a transistor, and then nanoparticles. And this starts to be the length scale that we look at in our lab, and you can go even smaller than that. So some even smaller items are DNA, and then small molecules, and then atoms. So basically all the work that I do is down over here. In this region is where I think, and we're talking about something, each of these is an order of magnitude, so very, very, very small. And why do we care about this sort of nanoscale, length scale, and these nanoscale materials? So a few examples. One is thinking about energy storage and battery materials. So this kind of is something that I started thinking about while I was working, but even though batteries are large scale devices and something that we have in our computers and our phones, it turns out that the really, really small features in our batteries on the nanoscale is what often impacts their performance. So we want to be able to look at those interfaces and characterize them. Kind of another topic is thinking about environmental remediation. If you think about wanting to clean something from the air or clean something from water, you want to make something that can absorb or remove something on that scale. So you want to design something of that size and be able to study what happens at that sort of scale. Kind of in a different direction, thinking about computers, trying to make them more energy efficient and faster and smaller. So we make smaller computer devices, and a lot of this relies on the idea of quantum. And then in a very different direction, also medicine and biotechnology and health. A lot of medicine and vaccine design comes from being able to kind of understand these different protein structures, and being able to image them is often used in vaccine development. So kind of what I hope you take away from this section is that we really, really care about nano to atomic scale materials, whether or not we're designing nano or atomic scale materials, or looking at bigger materials and wanting to look at their interfaces. So the tool that I use is really great for being able to image these really small lead scales. So in a scanning transmission electron microscope, you have a very small beam. When I line the microscope, it'll be anywhere from 1 or 2 nanometers to sub-angstrom, so less than 1/10 of a nanometer, because you want to be able to probe something on that size. And your electrons, you scan across your sample. On each position, you collect your signal. And most of your signal is actually what's coming through to the other side of your sample. So you want your material to be electron transparent. So your material is going to be less than about 100 nanometers thin usually. And you can do all kinds of different experiments in your microscope. So you can do imaging. So for example, here you can see the beautiful titanium structure on this graphene flake. You can do what's called diffraction. So this is sort of looking at the local arrangement or structure of your material at each position. You can study the composition, so look at what atoms are present. So here, for example, you see oxygen and manganese and lanthanum. And you can do all of this as what we would call in situ, but means just kind of observe things that are happening in real time. So you can apply stimuli like heating or cooling or biasing and see how things change, or even just leave them alone and see what happens. So in this image here, for example, you see gold nanoparticles that are sort of growing together, and you can observe this change. So it's pretty fun to see what happens. My PhD advisor said, you know, it's even fun to watch paint dry in the electron microscope, and I would agree. So this is kind of what you can do with your STEM, and this is what it actually looks like when you take images. So this is what I would call a lower magnification image. I'm looking at sort of one area, and then you can zoom in, and you can start to see my nanoparticles of interest. They have this nice rectangular structure, and you can go even higher magnification now, and really this is what the nanoparticles look like. And if you look over here in this image, you can see all of these different dots, and each one of those dots is a column of atoms. So that's what we're talking about here. We're doing like atomic imaging and probing the atomic structure of the materials, which is pretty cool. We see this all the time in the electron microscope. So this particular structure was a strontium terbium fluoride calcium fluoride structure. So it's 2 materials that are grown one on top of the other. And the collaborators I was working with at Berkeley wanted to be able to understand these materials and their interfaces and their structure. So this is why we did the really high resolution imaging. So I wanted to kind of paint you a picture of what we put in the microscope, all kinds of different things. So one project I did during my PhD was looking at human tooth enamel. People want to understand the structure. This is a pretty remarkable material. If you think about it, you chew every day, and you want to be able to see what's this material like, why is it so hard? And so you can kind of look at it on the nanoscale. It has these nanoscale crystallites. These are the smallest building blocks of it, but people really don't understand the structure very well. So this is where you can start to do some STEM imaging. So you can do a cross section of it and start to see its structure. This is a shell and a core and an intergranular region. So these images were taken by a group at another university, but we were working on some similar samples as well. In a totally different direction, you also can look at meteorites. So this is a project that I've been working on recently. You want to look at high pressure phases in meteorites. When they interact, you get these sort of shock veins. And you want to look at high pressure phases. So you can look at them with different types of electron microscopy and see these unusual phases and morphologies and be able to image them at very high resolutions. And then in yet another direction, you might want to be able to look at proteins. So this is a bacteriophage protein that we did some imaging of recently. And if we take just a few of these projections and combine them, you can solve for the 3D structure of these protein tails as well. So this is a few examples of things that I've looked at, but there's many, many more things that you can do. I wanted to show you kind of what the electron microscope actually looks like. So this is a STEM column. This is kind of a smaller one, but you can use the monitors here as a size gauge to see how big it is. It's a high vacuum. We do everything under vacuum. So you can see here at the top, we have our gun. This is our electron source. We load our sample, which I'll show you in a minute right here in the middle, and then below you have a lot of different detectors. So you can kind of image usually what's happening below. This is what a stem holder looks like. This is how you load your sample. So this is under vacuum, you have to get your sample to the center of this column. So you put your sample right here at the top, and you have this long rod that goes to the top. These sample holders are about this big, and the samples themselves look a lot like this. So they're about 3 millimeters in diameter, and then a few hundred nanometers thick. So you have to be pretty careful when you put it in the stem holder, and then you can put it in the electron microscope. And then you can start taking data. This is what it looks like when I'm taking data. So you can see this is the same nanoparticles, and you can see all the atoms here, this image, and the control panel down here. And then, of course, the most important part, you cannot do an experiment at NSEM without our post-spec Leo. So it's, again, an important part of doing experiments at NSEM. And kind of this is what we work on. So you might be wondering, this seems like it's pretty much already solved. You can see the atoms. What are you doing? What kind of stuff are you working on? So there's some challenges with kind of the conventional ways that we do imaging. One is you're using kind of a lot of electrons and a very high power source to do the imaging. So materials can damage when exposed to the electron beam. So this is the original image. And then you expose the sample to beam for just a little bit, and you start to get all these breaks in it. You want to be able to see the pristine sample, not the defected ones. So you want to be more efficient. Another challenge is contrast. So you can see here, I overlay where I think all the atoms should be in red and blue. And you can only see the red atoms in this image and not the blue atoms, right? And this is because we're sort of limited in contrast with conventional imaging modes, so you can't actually see where these blue atoms are, and that's something you want to work on. Another issue is that you're looking at something that's projected through your sample, right? So you kind of lose your 3D information and you get a projection artifact. And actually, this is something that's not just electron microscopy. You can see, for example, in this image here, there's 2 giraffes. And depending on how you look at them, it looks like maybe just 1 giraffe with 2 heads instead of 2 giraffes. So this is sort of a projection artifact we like to overcome. And the way that we're going to do this is with 40 stems. So if you bear with me for just a second and explain. So usually what we do is we have our probe and we scan across our sample, and we have these detectors. And at each position in real space, you get just one value. It's like an old TV. You raster across and you integrate all the signal, and whatever is there gives you an image. But if what we're going to do instead is replace that with a way to detect at every single position, a lot more scattering information. So if I play this movie now, you can see that as you scan across the sample and you sort of simulate what your electrons are doing below, you see this old detector here is lighting up every time it gets a signal, but all of this information down here is lost. We're not collecting that in the past. So what we do instead is we're going to have a special detector that collects all this information. And this hardware has sort of recently been developed to enable all this type of experiments. You can imagine now if you're scanning and taking a pattern and scanning and taking a pattern, you start to get a lot of data. So when we do this sort of experiment, we end up kind of collecting terabytes of data, and we have to think about analyzing it. So a big part of my job is not just sort of taking the data, but also thinking about how to analyze it. So what we do to work on that is we're developing a lot of open source code, and not just for our group, but kind of for other people to use as well. And the idea is you can analyze the data and be able to get back better images. We have lots of tutorials and we teach workshops. So here's a photo of us teaching at our workshop, and one of our workshop participants is here, which is George. So we do a lot of data analysis in addition to the experiments. So I wanted to show you just one example of why you might want to do this sort of complicated, computationally expensive, large data experiment instead of just conventional imaging. So I'm working with a group at Berkeley. This is with Dana, Byrne, and Francis Allen, and they want to take what's called a 2D material, so like a flat sheet, and make holes in it so you can use for environmental sensing and environmental filtration type applications. And so if you want to make holes to remove contaminants in the environment, as we talked about before, you want to have holes that are about the length scale of the things you're trying to remove. So these need to be about atomic defects. And if you did your conventional imaging of this material, once you form the defects, you want to see what it looks like. You can see one big defect here, maybe something here, but it's really hard to see what's going on. But if you do your complicated 40 stem analysis, it paints you a picture that looks like this, which is much better, right? Because now you can see all these single atom defects in your material, in addition to the much larger defect here. So this is why we go through all this trouble for doing this and work on development of experimental and computational methods for imaging. So that I have many people to thank. The people I work with at Berkeley Lab are my collaborators, and I thank you guys for your attention and for hosting this event. I'd be happy to take questions if people have them or anything like that, yeah.
Questions?
Don't see any on Zoom.
Yes, Dad.
Could you explain a word on your last slide, typographic?
Yes. So that's a good question, Dad. This is the method that we this is the name of the method that we use for sort of making these images from the 40-cent data set. It's called typography. And typography is sort of a way to solve an inverse scattering problem. So from all this data we collect and all these different patterns to get back an idea of what our sample looked like.
I would also love to know, so you have these images now, do you like, once you have those images, do you like send it to the people who manufacture it and say, hey, you messed up here, 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 and here, or like what do you do then with the images once you produce them?
It depends. We usually work with the people who are making the material, so they come with a certain specific research question about wanting to know, in this case, you could say, this is what your defects actually look like, so you might want to change how you're forming them. Or people say, I came and my material looks like this, and put it in the microscope and say, it's not what it looks like, or something like that, it's kind of an iterative process usually with people to go back and forth, because it's, if you think back to the first slide where we talked about nanoscale, length scale, it's really hard to know what something looks like from just looking at it. So yeah, kind of an iterative design process is best case. Yeah.
When you're doing something like this, how can you tell when a defect is caused by the microscope itself?
That is a really good question. So you can't, right? You are using a really high powered electron beam and it creates defects in the material itself. So kind of, you can do some controls, you can image multiple times and see if things change. But that's a huge problem, right? You never know if what you're looking at was caused from electron beam damage, or preparing those special samples that are really, really thin, right? Also create all kinds of defects. Yeah, this is a big concern.
Well, there was another word, tero something.
Oh, terabytes. Yeah. So it's like,
What was it?
like just a lot of data.
Okay.
Yeah. Like maybe your computer holds a few hundred megabytes of data or a terabyte of data or 2 terabytes of data, depending on the type of computer you use. So like as much memory as would fill a laptop in a day.
Gotcha.
Yeah.
Don't see any questions online, so.
Oh,
What's next in electron microscopy? What's the next frontier in microscopy?
That's
And also, yeah.
Yeah, that's a good question. Maybe you should tell me. I think that both in terms of more computations, so kind of more advanced computation, making these methods more deployable, we're getting more and more data, right, with more different types of detectors and being able to do more automation and combining those signals. And then also on the other side, making things much more widely usable. It's awesome that we have this center that's kind of free to use, that people can come visit, but also our time on the microscope is pretty limited, right? So making things cheaper, more easy to use, simple, more straightforward imaging. Yeah, that's a great question.
Let's thank Stephanie one more time.
Okay, great. And now we go on a totally different length scale, I think.
Very different.
Like 2 length scales of astronomy. And did you have?
Oh, just one with the duck obsession.
Oh, yeah. Good question.
Sorry, I'm sorry.
While our next speaker sets up, I want to thank Stephanie again for the really cool talk. And I'm going to introduce our next speaker, Natalie LeBaron. Natalie completed a BS degree in physics at UC Santa Barbara in 2022 and is now a rising third-year PhD student in the UC Berkeley Astronomy department. She is an observer studying transients, including supernova and other rare high energy explosions. So take it away.
So thank you for the introduction. yeah, thank you for the introduction. As Elsie. Caitlin. Caitlin said, I'm Natalie. I'm a third year grad student here at Berkeley, and I study explosions. So, yeah, what I want to talk to you about today is,
You still need to share.
oh,
Sure.
thank you for the reminder. All right, so yes. So what I want to talk a little bit about today is basically what I study, more emphasis on the death of stars than life, but life also goes into it, and specifically where the elements that make our world form. So to start, this is basically a picture of our solar system. So how much of each individual element is part of our solar system. You can see a lot of hydrogen and helium, very little of heavier elements like lead or uranium, or even fairly light elements like lithium. And question is, well, why is our solar system this way? How did it get, or how did these elements form? How did they get into the solar system? And why this specific composition? I'll answer at least some of those questions today. So the interesting thing is, of course, that there is so much hydrogen and helium compared to everything else. And actually, well, we know that we have this periodic table that tells us basically everything that, well, I guess the best way to explain this slide is that this is the summary of my talk that I'm putting here at the beginning to show you where we're going. And yeah, basically this sums up everything that I'm going to talk about today. Hydrogen and helium make up the majority of our universe. So about 75% of our universe is hydrogen, another 24% is helium, and everything else that we see in the periodic table, and maybe what we think more about in our daily lives, is basically that 2%, which is crazy if you think about it. So where does all this hydrogen and helium come from? Well, comes from the Big Bang, mostly. So right after the Big Bang, universe is basically this really hot soup of electrons, photons, and these things called quarks, which are the constituent particles that make up things like protons and neutrons, which, if you remember high school chemistry, form the atoms that make up all the elements in our world. So right after the Big Bang, it's really hot, and these quarks can't form together. It actually takes about not too long, only about a microsecond, for the universe to cool off enough for protons to actually be formed. But still, the universe is way too hot. Electrons cannot basically come together with those protons and create the neutral atoms that we assume or think about in our daily lives. So if you've ever like rubbed your hair and gotten a shock when you touch something metal, that rubbing your hair basically pulls off all the electrons that are on the atoms, or at least some electrons on the atoms that make up your hair. And you get these things called ions, which are basically protons or nuclei that are missing some of their electrons. So they're a little bit positively charged. So that's essentially what the universe looks like up until about 400,000 years after the Big Bang, when something called recombination happened. So this is when the universe cools off enough and electrons can actually rejoin or recombine with protons to form neutral atoms. It's actually the first combination, but we call it recombination for some reason. First thing, or first example in this talk where astronomers, shall we say, name things before they actually understand what they are. So basically, what's happening before recombination is protons are forming. Protons are just hydrogen atoms, but ionized. So this is the period where basically all the hydrogen that exists in our universe is formed. Along with that is some helium and lithium. Helium and lithium are just more protons shoved together to make bigger atoms, or bigger atoms and different elements. So the majority of the hydrogen and helium in our universe comes from this period before recombination, also a little bit of lithium. And the way that that works, that you make bigger elements than just hydrogen is, well, we know from just like playing with magnets, like charges repel, right? So it's really hard to force two things that are positively charged together. That works the same for protons. Protons don't like being forced together, but when you're in this really hot and dense period in the universe, it's actually hot and dense enough such that at least some of protons can come together and fuse into heavier atoms like helium. So that's essentially how you get helium and a little bit of lithium in the beginning of the universe. However, after recombination, the universe is no longer hot and dense, or at least it isn't as hot and dense. So you have all these neutral atoms floating around in space. And the question becomes, well, we know that other things exist, right? We have this entire periodic table. So where do these heavier elements form? Well, where is a place in the universe that is hot and dense enough to fuse more protons together? Needs to be something in our own backyard. So stars like our sun are actually hot and dense enough such that in their pores especially, they can fuse together protons and even heavier elements later in their lives to form bigger elements. And the great thing is that fusion, especially for small elements, is energy positive. So you might have this big ball of stuff that's like pushing down with gravity, but you have energy from these fusion reactions that is actually pushing to keep the star afloat, basically, against gravity. So it's a really cool thing. It essentially comes from quantum mechanics that actually enables most of life, or most of the universe that we know. So yeah, so stars start in these big clouds called stellar nurseries, or just certain types of nebulae, which will collapse down and create stars. So you go from these really big things, if there's like an overdensity in the big nebula, they'll start collapsing towards the center of those overdensities, and eventually you'll end up with something that has a core that is dense and hot enough that it'll start fusing hydrogen and helium, which is what we call a living star. So stars will be born somewhere on what we call the main sequence. So that's this big line through the middle. And they will live most of their lives on that main sequence, using, again, hydrogen into helium, and being quite happy to stay there and just do their thing. However, there's only a finite amount of hydrogen in their cores, and eventually all of that will be fused together into helium, and the star will use the energy support that it needs against gravity. So at that point, gravity will start pushing down and essentially collapsing the star until another source of power is turned on. There are two main paths to stellar evolution. So you either have low mass stars like our sun that follow their own evolutionary track, or massive stars that are about 8 to 10 times the mass of our sun that follow another track. And we'll see how they kind of differ in how they evolve. So let's start with our sun. So as I said, our sun or other low mass stars like it will start by collapsing a big cloud of gas into a protostar. They'll be born onto the main sequence. Our sun is a G-type star, and you can see that for most of its life, the sun will just live there on the main sequence. After about some number of billion years, low mass stars will use up all of their hydrogen reserves, and as I said, their cores will start collapsing under their own weight. At the same time, the outer layers start puffing up while that core is getting denser and denser, and you'll get a red giant star. So in the cores of these red giants, at some point, they'll get dense and hot enough to be able to fuse helium into heavier elements. So that will supply the energy needed to protect the star for a while against gravity collapsing it any further. So stars like our sun will exist as red giants for a while. And to give you a sense of scale for how big these things get, our sun should get about, so our sun should become about the radius of the Earth's orbit around the sun. So that should be in another 4 billion years or so. And, humans are around that. I'm sure we'll figure something out, but much after any of our lifetimes. So the sun will exist as a red giant for a while, and then eventually the outer layers will slough off enough that only the core remains as a white dwarf, which is basically just the ashes of whatever the star couldn't get dense and hot enough to burn. For most low mass stars, you can get up to about maybe carbon oxygen core. And what'll happen is that as it contracts, you'll get different layers starting to fuse at different times. So if all the hydrogen has been used up in the center, it'll contract until helium ignites, but along the way, shells that are around or a little bit further up from the core will start to burn along the way. But eventually you end up with a white dwarf. So usually just like carbon oxygen ashes, maybe neon if you're big enough white dwarf or big enough progenitor star. And these things basically just sit there and cool off for the rest of time. In the meantime, they do let off their outer layers of the star in these beautiful nebulae. These are called planetary nebula, or the second example of astronomers knowing nothing about what they're actually naming. But they do look beautiful, and all of them will have a white dwarf in the center. Of course, after time, you may not be able to see that white dwarf since it's cooled off so much. So these low mass stars will produce things like lithium and carbon and nitrogen, since that's what's in their outer layers that gets sloughed off. Usually the core will just kind of stay there. But as you can see, dying low mass stars also seem to produce some of these heavier elements like lead or zirconium. And the way they do that is that when they start evolving off main sequence, they go kind of up this way into the red giant branch or asymptotic red giant branch. And interesting thing about these type of stars is that they're really neutron rich in their outer layers. So what can happen is neutrons are charged neutral, so they can enter a nucleus of an atom without worrying about charges repelling or anything. But neutrons are actually slightly unstable. So if a neutron goes into a nucleus and then decays, it'll actually decay into a proton. So have another proton means you have a bigger element. So this is a way of making bigger and bigger elements and filling out that part of the periodic table. So the way that it happens is that basically this shows number of protons versus number of neutrons in a nucleus. That the black line in the center of all the colors is this thing called the valley of stability. So it's where all the stable nuclei live. So if you say take a stable nucleus and add another neutron, it will end up decaying back into the valley of stability by turning that neutron into a proton. Similar other types of decay happen if you say like add another proton somehow to a nucleus, and other effects happen when you get to really, really heavy nuclei. But basically, you always end up somewhere near the valley of stability. And that's essentially how we make a lot of these heavier elements that are colored in yellow. So talk about these white dwarfs. So white dwarfs are these really ultra compact stellar remnants. They're basically held up by the Pauli exclusion principle. If you remember your chemistry, it's basically that their quantum mechanics says that you can only pack so many electrons into such a into a certain amount of space. So these white dwarfs, they have no power source that's keeping them from collapsing, other than they're so dense that the Pauli exclusion principle starts saying that you can't actually fit any more electrons into this space. So they're held up by this thing called degeneracy pressure due to electrons, which is pretty cool. And in most cases, they're happy to just, again, live out their lives. However, they are degenerate. So basically, if you add more mass than about a solar mass worth of stuff to a white dwarf, it won't be able to stay stable against gravity. So what that means is that if you have a solar system that has, say, 2 stars in it, so it's a binary system, trinary system or something, actually serious here. So this is a main sequence star and its little white dwarf companion. If you have multiple stars in a solar system, you can have mass transfer onto that white dwarf. So for example, if you have 2 white dwarfs that live out their lives independently and then continue orbiting each other until they merge, that will, in a lot of cases, bring you over the mass limit for a stable white dwarf. Or if you're in a white dwarf plus main sequence star system, that white dwarf can actually steal mass from the main sequence star. And what happens is when you get over a little over 1.5 solar masses, is that the white dwarf becomes really unstable and it explodes as what we call a type 1a supernova. So this is a picture of a 1a supernova in the Pinwheel galaxy taken in 2011. You see there's no star here. There very much is in those 2 other pictures. And yeah, that's basically the end of some white dwarfs if they're in a system that can actually accrete enough mass to do that. And 1A supernovae produce a lot of our iron peak elements. So you can see that all these blue elements are predominantly created in these white dwarf explosions. And especially the nickel and cobalt decay power how long the supernova stays bright in the sky. Okay. So let's talk about massive stars. So massive stars do kind of the same thing as low mass stars. They are born onto the main sequence. They live for a long time, a much shorter time than low mass stars, but still, millions of years. And once they start evolving off the main sequence, they are able to get more dense and hot than low mass stars. So they're actually able to fuse bigger and bigger elements. So you end up with this onion-like structure where basically each ring is the ashes of the last ring that could fuse in the center before the star had to get more dense in order to fuse the next heavy element. And this is fine and well. It goes on for a decent amount of time, but at some point, it doesn't work so well. So fusion is this great thing that releases energy when you put two nuclei together. But as you get to bigger and bigger nuclei, they're diminishing returns. So for example, hydrogen, if you push two hydrogen atoms together, you get out a lot of energy. If you try and push together bigger and bigger atoms, you get some energy, but less than hydrogen. So that's kind of what this average binding energy per nucleon is telling you. Basically, as you get higher and higher, you're releasing less energy for each fusion reaction, which is a problem when the star is still as massive as it always was and still needs the same amount of energy to support itself against gravity. So this all culminates in when the core starts to become iron. So the star will fuse all the way up until basically the core becomes iron rich, since iron is the first element for which you do not get energy out when you fuse iron atoms together. So this is kind of the difference between fusion and fission. So when you have these big heavy nuclei like iron, but more efficiently something like uranium or some other big heavy nucleus, you break apart uranium, you get out a lot of energy. That's the opposite with smaller elements. So the real, that's why when you look at the core of these massive stars, we end up with an inert iron core that is not going to fuse together and create energy, which is a problem, of course, since you still have gravity and you still have all this material that is trying to collapse and, condense down into some kind of remnant. So once you get to iron, you get what's called a core collapse supernova. So the star is no longer able to support itself. It actually kind of bounces off the inert iron core, and you get all these effects which lead to this giant runaway reaction that results in this beautiful flash of light that is what I study most days. So this is a supernova actually that happened in the Pineal Galaxy last year. Very exciting. It's a very close supernova, as was the one in 2011, but it's more interesting to me and my group. But so get these very cool pictures, which I think any astronomy presentation would be remiss without. This is another famous supernova, and actually the Large Magellanic Cloud, even closer than the Pineal Galaxy from 1987. And you've had these big explosions and they leave behind these beautiful remnants. So these are a couple of supernova remnants of the Crab Nebula and this other one that I forget the name of, but some of the prettiest things in the sky, I would say. And all of these nebulae, supernova remnants, will have some kind of supernova compact or remnant compact object in the center of them. So you either get out something called a neutron star, which is similar to a white dwarf in some respects, in that it's held up by neutron degeneracy pressure, or a black hole, which is sort of like the ultimate dense thing that you can get out of universe. So there's another supernova, and basically these supernova also produce a lot of elements, especially the sort of lower mass elements, or mid mass elements maybe. And they leave behind these cool nebulae and these remnants that have very cool implications for the last part of the periodic table that I'm going to touch on. So you have, for example, a binary system with 2 supernovae. You can potentially get out 2 neutron stars or a neutron star and a black hole that are orbiting around each other. And these are some of the, I'm somewhat biased, but coolest events in the universe is when these compact objects merge. They also create the highest energy events in the universe. So these gamma ray bursts. And if you talked to someone in my field 10 years ago, the periodic table that I showed you would be completely different, because we actually observed a neutron star merger for the first time in 2017. So this is a graph of the signal that LIGO, which is Gravitational Wave Observatory, found, that was able to be followed up and found in the optical very close in, I guess, transient astronomy terms to us. So this is what we call a kilonova. Kilonova are very cool because they're very neutron rich, being neutron stars, and will do this thing called rapid neutron capture nucleosynthesis. So this is similar to what I was talking about earlier with neutron capture in red giant stars, but this happens on a much faster time scale, which means that you can create much bigger nuclei out of this. So that's essentially how you create really big nuclei like uranium, like gold, and a bunch of the big heavy elements, actinides and lanthanides on your periodic table. So that mostly sums up my presentation. The work that I do as a grad student is basically, one part of it is looking for other sites where this rapid neutron capture nucleosynthesis and these big heavy elements can be made. So for example, and I'm trying to understand whether certain types of supernovae, which have similarities to kilonova, whether they can actually produce these lanthanides and actinides. And yeah, that's most of my presentation. If you have any questions, I'm happy to take any.
For Natalie.
Yes.
Thank you for the talk. I'm curious what the deal is with lithium. Looks like
Yeah.
it's like an anomaly in most
Yeah.
graphs.
Yeah, so actually I have so lithium and beryllium. So beryllium's pretty radioactive. It doesn't stay around for very long, but lithium and those couple elements that are very low population are basically created by cosmic ray fission. So basically you take a big nucleus and you shoot something at it and it breaks apart and you get smaller elements. So as you can imagine, it's hard to necessarily end up with just 3 protons.
Why is it so hard to fuse? Like, why is that an anomaly in the energy?
Yeah, that's a question for someone who studies actual atomic structure. I don't do that. Yeah.
How do you know where to take data? Like the sky is so big, right? So
That's
how
a
do you
great
know
question.
where to look?
Yeah, so there are actually big surveys that are like always scanning the sky. And a lot of them are kind enough to publish when something changes and kind of goes out into the community. So like you start out with big surveys on telescopes. Some of these do that. None of these are really survey telescopes here, but things like them will scan the sky every night and basically compare that to historical data, and then you know where to go to look for things. The harder part is knowing which ones of those to follow up, because there's lots and lots of candidates every single night. So the question is, you know, what's interesting, and especially in this day and age where we have these automated surveys, you know, how do you scan through things and figure out what's real, what's not real, what's interesting, what can be feasibly followed up with the resources and time that you have. And that's some of what I do, is figure out what things are interesting to follow up and get resources to follow those things up on telescopes like these. Question?
Hi, with the greenhouse effect, have you or has anybody noticed any changes with the stars around Earth's kind of orbit? Yeah.
So the closest star that we have to ourselves is the sun. The sun isn't really affected by anything on Earth. It's too far away and too big to really be affected by anything that we do here. Closest solar system to us is, 4 light years, which is very far. So nothing really affecting the stars themselves. Affecting observations, definitely. Like weather certainly affects our ability to observe things. And if we have a climate that's more variable and more inclement weather, then that certainly affects. Also, satellites are bad for observations, because you can imagine it gets in the way. Other questions? Yeah.
How do you come up with the criteria, like in terms of which one to follow this observation? Is that like part of a theory, or you have a based on heuristics, or you just have some hunch? I guess it's like dark art.
To some degree, like there's certainly skills to learn to do it, but a lot of it is just that we have these big collaborations that like their job is to identify things that are interesting. So I guess the first level is these days we have algorithms that will go in and or figure out what is more likely to be real and not like an imaging artifact or a satellite or something like that. And then after that, we have some idea of what certain things look like. So for example, a supernova has maybe not a totally distinct light curve, but like a fairly distinct light curve if you get enough observations over enough nights. You can kind of tell that it's going to be something that's interesting. A lot of stuff is too dim to follow up in a reasonable amount of time. A lot of stuff, stars will go behind the sun and then you can't observe them for a couple months. So there's planning associated with that too. But the real nice thing is that people actually make it their jobs to go out and take spectra of interesting objects, which will specifically tell you what they are. And from there, you can choose which ones you're interested in. So
Sorry to, yeah, piggyback on the question, because I feel like there must be like, based on lots of experience, also luck. Because I was thinking about analogy, the ones up the hill, the Lord's library, they were like once discovered just some accounting error, like 25 cents or not. And then lead to discover the Soviet Union was doing intrusion, attack on the network, on the sort of the what the national labs. So that because that person was really familiar with the activity, has like a bonding experience. So that's because that's my background. I'm just thinking about that promise, and
it's definitely a lot of luck in it too, especially in the transients field. You can't really choose what the universe is going to give you on a given night.
A question for you. So you've mentioned partnerships and satellites. Are there any like NASA news stories or projects that you're following, or it doesn't have to be related to this, but that you just find really interesting?
Recently, recent. The one that comes to mind is last year we put out actually some people in my group were part of this, and people at Berkeley who do transients put out a notice about the second supernova that I showed you in the Pineal Galaxy. That was actually almost discovered by Alex Filipenko. He was actually observing that night with his little amateur telescope, but it was officially discovered by a Japanese astronomer who actually is someone who tells us a lot when there are supernovae.
That's cool. And for anyone who's looking for amateur telescopes, we do have one that circulates in the library. You can put it on hold and catalog and check it out. I personally brought it to Death Valley before and enjoyed it. So yeah, awesome. Yeah.
Can also do a quick plug that at the UC Berkeley Astro Department, we have Astro Night, which is the first Thursday of every month, where after a public lecture, there's stargazing for the public. We take you up to the 6th floor of Campbell Hall over there, it's the department, and you get to look through some big telescopes that we have too. So
first Thursday every month.
Next
First
one is
Thursday.
September 5th.
yeah, if you just look up UCB Astro Night, should be one of the first things that pops up.
Is that on the events calendar?
On the Astro Department website, yeah.
Should be on the campus list.
I don't know about campus ones, but.
Maybe something for us to figure out.
Oh, yeah.
Yeah. Cool. Anyway, thank you so much.
Alright. And as promised for the finale, I will show you the fancy QR code that we have if you wish to sign up for our listserv here.
And it's a great listserv. Often the scientists will talk a little more about their research. You get a little extra content. And I really encourage folks to check out that YouTube channel as well. We started archiving talks during the pandemic. So there's quite a few years of talks on there.
Yes, we're definitely certainly building up quite a bit of literature that we have on the YouTube page now. So here's the QR code, or if you don't have camera or anything right now, it's just bit.ly/TTSB emails. You can sign up there. The YouTube channel is linked just over there. Our next seminar will be the 3rd Tuesday of September, which is September 17th. I don't know if we have.
Tentatively, our talks will be on protein voting and I think another material science talk. But we will send out an email to the list.
So we hope to see you then. Thank you again for coming out. And let's do one more round of applause for both.
Thank you.
Have a great night.
Have a good night.
Thank you for coming. All right.
I'll leave that up.
We've got